Tonight, we quietly consider one of the stranger truths about the particular corner of space we inhabit, a direction almost nothing has ever gone. Straight up, straight down, away from the flat, shared plane that all our planets call home. Of every image humanity has ever assembled of the cosmos around us, the one photograph we are still missing is the simplest to describe and the hardest to obtain. A view looking straight down at our own solar system from above it. What stands between us and that picture is not the vastness of distance, and it is not a failure of imagination. It is the quiet, elegant, completely indifferent fact that every spacecraft we have ever launched was already moving sideways when it left the ground, already swept up in the same long orbital current that has carried everything in this system for 4.5 billion years. Over the next 2 hours or so, we will gently wander through what waits in those directions we have barely visited, what the sun looks like from angles we have almost never seen it from, what the boundary of our own solar bubble might look like from outside the disk that contains it, and the curious falling toward the sun maneuver that may, one day, allow a spacecraft to finally make the climb. If any of this feels worth your while, a like or a subscribe helps quietly extend the channel's reach to others who might enjoy it. Truly, thank you for being here. But tonight, none of this requires anything from you. You can set down whatever you were carrying today. Let your shoulders find their natural resting place. Let your breath find its own easy rhythm. Let the last of the day dissolve. We can begin. There is a simple, rather overlooked fact about where we live that shapes every image of the night sky ever recorded. Our solar system is not a loosely assembled sphere of orbits, nor is it some scattered cloud of wandering bodies. It is a disk, a wide, gently rotating, remarkably thin disk of planets and moons and comets and dust, all sharing the same gentle plane, all curving around the same central star, all caught in the same patient sideways motion that has persisted for 4.5 billion years. The sun sits at the calm center of that disk. The planets trace out its inner rings, and the direction perpendicular to the disk, the direction we might think of casually as simply up or simply down, is a direction in which almost nothing familiar to us has ever traveled. The flatness of the solar system is arguably the most significant geometric fact about our home. It is also one of the least remarked upon, because nearly every illustration of the planets we grew up with either shows the disk from the side, where the flatness is so obvious it seems unremarkable, or from above, where it is treated as the obvious starting arrangement, rather than as the quietly remarkable thing it actually is. Standing on Earth, the disk announces itself everywhere you look. The sun traces a consistent arc across the sky each day. The moon follows roughly the same path. The planets drift along the same gentle curve overhead. Every light we recognize in the night sky, apart from the distant fixed stars behind it all, moves along a single imaginary line called the ecliptic. The ecliptic is nothing more than our view of the disk from inside it, the line along which all the familiar inhabitants of our solar system can reliably be found. The flatness is not an accident, and it is not the result of any particular arrangement. It is a fossil, preserved in geometry, of the way our solar system came to be. The idea behind it is one of the most graceful in all of modern astronomy, and it is worth settling into slowly. Picture a vast, slowly turning cloud of gas and dust drifting through interstellar space, a cloud far wider than any planetary system. Gravity draws the cloud inward, but the cloud is also spinning, and rotation, once acquired, is not easily abandoned. The cloud can collapse freely in the direction along its spin axis, because nothing resists that collapse. But it cannot collapse across the axis without first somehow giving up the spin that holds it wide. Given enough time, the cloud flattens. The dimension parallel to the spin axis shrinks. The dimension perpendicular to it persists. What was once a cloud becomes a disk. A young sun coalesces at the disk's center, drawing in most of the material. The surrounding disk cools. Heavier elements settle into tiny solid grains. The grains accumulate. The growing clumps sweep up still more material as they orbit. Planets assemble themselves within the plane of the disk, inheriting its geometry as naturally as water inherits the shape of a bowl. Any material that wanders too far above or below the plane is either pulled back by the disk's collective gravity, flung outward and lost, or simply never finds enough company to accumulate into anything at all. The angular momentum the original cloud possessed becomes the long sideways motion that keeps the disk spread across light hours of space. The disk itself, the protoplanetary disk, has long since dispersed, swept away by the young sun's radiation. But the planets remain exactly where the disk once was, orbiting the plane it once defined. This same interplay of rotation and gravity produces disks at every scale where both forces are present together. The rings of Saturn are a small, intimate disk. The Milky Way galaxy is a vast one. The swirling material being pulled toward a black hole arranges itself into a disk as well, governed by precisely the same physics, rotating, contracting, flattening, holding itself wide through angular momentum, while collapsing freely along its poles. A spherical solar system would be the genuinely surprising outcome. A disk is simply what gravity and rotation, given time, almost always produce. The plane the solar system settled into has a formal name: the invariable plane. It represents the weighted average of all the planetary orbits, with the most massive planets contributing most heavily to the calculation. Jupiter, being by far the most massive planet, has an outsized influence on where the invariable plane sits. Our own orbit, the one the listener is presently riding on, is tilted by only about 1.5 degrees relative to this invariable plane. A difference small enough that the plane of Earth's orbit, the ecliptic, is usually treated as if it simply were the plane of the solar system for most practical purposes. The majority of the solar system's major inhabitants orbit within just a few degrees of the ecliptic. Mercury sits at about 7 degrees. Venus and Mars and the outer giants cluster even closer to it. Pluto, the most famous exception, tilts at about 17 degrees, giving its orbit a noticeable rise and fall above and below the central plane. A handful of smaller icy bodies out beyond Neptune tilt more steeply. The long-period comets, arriving from enormous distances, can plunge in at almost any angle before sweeping back out again. But these are variations on a fundamentally flat theme. The overwhelming majority of what orbits the sun does so within a narrow band of sky. The disk did not fully disappear when the planets finished forming. A faint, diffuse residue of fine dust still clings to the plane, replenished continuously by the ordinary processes of the solar system itself. Asteroid collisions, happening quietly and persistently in the belt between Mars and Jupiter, grind material into ever finer grains, eventually down to motes measured in microns. Comets shed material as they swing through the inner system. The slow erosion of icy bodies at the solar system's outer edges adds its own small contribution. All of this dust settles toward the plane because its sources live in the plane. and the combined influence of sunlight pressure and planetary gravity keeps it there. The result is a thin, faintly luminous sheet of dust that continues to mark the geometry of the solar system long after the original formation disk has gone. On a sufficiently dark, clear night, far from city light, this dust can actually be seen with the naked eye. It appears as a soft, tilted cone of pale light rising from the horizon after sunset, or reaching up from the horizon just before dawn, following the line of the ecliptic. This is called the zodiacal light, named for the zodiacal constellations that run along the ecliptic. What we see is ordinary sunlight scattered back toward us by the dust of the plane. It is not a phenomenon of our atmosphere, and it is not an aurora. It is the disk of the solar system itself, made faintly visible by the sun's reflected light. To see it is to see with unaided eyes the geometry of the place we live. The dust of the zodiacal cloud is densest close to the sun, thinning gradually with distance outward, and thinning quickly in the perpendicular direction, above and below the plane. There is a somewhat brighter contribution near the asteroid belt, where collisions are most frequent, and a fainter outer contribution from the icy bodies far beyond Neptune. Seen from inside the plane, this forms a soft, diffuse glow along one band of sky. Seen from above, it would appear as a wide, flat sheet, with the planets threading through it like beads drawn slowly along their paths. The inner regions glow more brightly. The outer regions fade into the background. This geometry of dust is part of why the vertical axis of the solar system feels so remote in spirit, even if not in physical distance. Looking along the plane, the line of sight passes through layer upon layer of dust, scattered sunlight, and the accumulated local light of the solar system itself. Looking perpendicular to the plane, directly above the sun's north pole or below its south, almost none of this dust intervenes. Those directions offer some of the cleanest views of the wider universe available from anywhere inside our local system. The disk that holds our home is also what crowds the rest of the sky. The directions where the solar system is least present are the directions perpendicular to it. If you have spent time watching planets, noticing that Venus and Jupiter tend to occupy the same invisible curved line in the sky, or that the moon a few nights later follows the same arc, you are already tracing the ecliptic with your eyes, without necessarily naming it. The planets do not scatter across random directions because they all inhabit the same plane. The arc they trace is simply the disk seen edge on from our vantage within it. Astronomers work with two main coordinate systems for describing positions in the sky, both shaped by the geometry of our immediate neighborhood. One uses Earth's equator, projected outward as a reference. The other uses the ecliptic itself. These two planes are tilted relative to each other by about 23.5 degrees, the same tilt that gives Earth its seasons, since our rotation axis looms rather than standing straight up relative to our orbital plane. The two planes intersect at 2 points called the equinoxes. For tonight's purposes, the essential feeling is simpler than the coordinate geometry. There is one natural plane in the solar system. All the planets share it, and the direction perpendicular to it is one in which almost nothing in our experience has ever pointed. The disk of our solar system is itself nested within a much larger disk, the disk of the Milky Way galaxy. The Milky Way is a slowly spinning spiral, hundreds of thousands of light years across, made of several 100 billion stars, along with vast amounts of gas, dust, and dark matter. Its shape, like the shape of the solar system, is a fossil of its long rotation.
flattened over immense stretches of time. But the two disks do not share the same orientation. They are tilted with respect to each other by roughly 60 degrees. The Sun and its family of planets orbit the galactic center in their own private plane, oriented quite differently from the plane of the galaxy as a whole.
This difference is barely perceptible from inside the solar system, but it becomes significant when imagining what the sky looks like from above the Sun. From Earth, the band of the Milky Way arcs across the night sky, with the bright central bulge most visible from southern latitudes during certain months. From a vantage point directly above the Sun's north pole, that band would tilt sharply. The galactic center's bright bulge would lie in a different direction relative to the ecliptic. The familiar arrangement of the southern sky's constellations, the dark dust lanes threading through the band, the soft glow of the galactic core, all of it would appear from such a vantage in a geometric arrangement that feels almost entirely unfamiliar, even though the stars themselves are unchanged. The same sky, seen from somewhere we have never stood, would present a different face. The Sun is also moving through the galaxy, carrying its planets along with it, at roughly 200 kilometers per second relative to the average motion of nearby stars. The direction of this drift points toward a patch of sky in the constellation Hercules. Over the full history of the solar system, this drift has swept the Sun through an enormous volume of the galaxy, through denser regions and quieter ones, through the galaxy's spiral arms and the quieter spaces between them. The Sun currently travels through a relatively low-density region of interstellar gas known as the local bubble, a space thought to have been carved out by ancient supernova explosions. The direction below the Sun's south pole, in galactic terms, opens into one of the clearer sight lines through this region. The plane of the planets, the plane of the galaxy, and the directions perpendicular to each of them all intersect across the same patch of sky we observe every night. We live at a meeting point of multiple flatnesses, multiple long-settled rotations, multiple layers of organized structure. The geometry of where we are is not arbitrary. It is the layered consequence of clouds once contracting, gravity once organizing, and rotation once imposing its preferences across time. The simplest single fact that makes the rest of tonight cohere is that the solar system is flat. The disk is real. The vertical axis is real. And what follows from here is a long, unhurried consideration of how rarely we have ever looked along that vertical axis and what might greet us if we did. There is an important truth about the act of leaving Earth that is rarely stated plainly outside of the rooms where missions are actually designed. We are not resting still. The ground beneath you is moving, not because of any tremor or local motion, but because the entire planet is sweeping sideways around the Sun at a speed so constant and so steady that it produces no sensation at all. Earth's orbital speed is roughly 30 kilometers per second. In each second, the planet covers 30 kilometers. In each minute, 1,800 kilometers. In each hour, more than 100,000 kilometers. Everything on this planet, the listener, the room they are in, the building, the air, the seas, the bedrock, the molten interior below it, all share exactly the same enormous sideways motion.
A rocket lifting off from a launch pad inherits all of that sideways motion the moment it clears the ground. It does not have to generate the velocity from nothing. It arrives in space already moving at 30 kilometers per second around the sun simply by virtue of having been on Earth. What the rocket must add to achieve orbit around Earth is a further roughly 8 kilometers per second relative to Earth's surface. What it needs beyond that to reach the Moon or Mars or Jupiter is comparatively modest, because the sun's gravity already governs the broad shape of those journeys. The rocket is essentially adjusting an existing orbit into a new one. Nothing it does erases the sideways motion around the sun it was born with. Nothing it can do returns it to a state of rest relative to the sun. This inheritance, this birthright of sideways motion, is the reason almost every spacecraft ever launched has ended up traveling more or less within the plane of the planets, and why almost nothing has ever moved meaningfully above or below that plane. To climb above the ecliptic, a spacecraft does not simply need to point upward and accelerate. It needs to erase the 30 kilometers per second sideways motion it began with and replace it with an equivalent motion pointing perpendicular to that plane. The disk is not a road, it is a current. Everything within it is being continuously swept along the same direction, and redirecting that motion is enormously more costly than simply continuing to follow it. Mission planners use a specific term for the total capacity a spacecraft has to change its own velocity over the course of a mission. They call it delta V, the change in velocity available from its onboard fuel. Delta V is, in a sense, the currency of movement through the solar system. Each maneuver spends some. When the budget is exhausted, the spacecraft moves as gravity moves it, and no other way. How large the budget can be depends on how much fuel was launched and how efficiently the engines convert that fuel into motion.
The chemical rockets that have lifted spacecraft off Earth over the last 7 decades have specific efficiencies that define practical ceilings on how much delta V any given mission can carry. To give a sense of the relevant numbers, reaching low Earth orbit from the ground requires roughly 9 to 10 kilometers per second of delta V, most of it spent fighting gravity and drag during the early climb and building the sideways speed needed to stay in orbit. From Earth orbit, reaching the Moon requires another 3 or 4 kilometers per second. A favorable trajectory to Mars costs roughly 4 kilometers per second beyond Earth orbit. A trajectory to Jupiter, using the most energy-efficient path and a good launch window, costs roughly 6.5 kilometers per second beyond Earth orbit. These are familiar destinations, and modern rockets are entirely capable of delivering spacecraft to them, given careful mission design. A trajectory aimed directly out of the plane of the solar system, one that would climb perpendicular to the ecliptic into the empty sky above or below, requires erasing most of Earth's sideways orbital motion and substituting an equivalent speed pointing straight up. The delta V cost from low Earth orbit is roughly 30 kilometers per second. No chemical rocket has ever delivered anything close to that figure to a single spacecraft. The largest interplanetary missions ever flown have carried total delta V budgets in the range of 15 to 20 kilometers per second across their entire operational lives, most of it used to enter orbit around a destination or to adjust trajectories at arrival. The direct path out of the plane is not merely ambitious, it is categorically out of reach for the rockets we build. Sit with the quiet strangeness of these numbers for a moment. Sending a spacecraft all the way to Pluto at the distant outer edge of the planetary system costs less delta V than sending that same spacecraft directly upward, perpendicular to the plane, to a height no greater than Earth's own orbital distance. The journey to the edge of the planetary disk is genuinely easier in fuel terms than the climb to the empty space immediately above the sun. The plane is not a path we drive along. It is a current we are carried in, and the current has been flowing in the same direction for billions of years. Stepping out of it sideways is not a matter of adding thrust. It is a matter of first undoing billions of years of built-in motion before you can begin. The reason this priority ordering feels so counterintuitive comes down to geometry. To travel outward, to Pluto, to Saturn, to the edge of the system, a spacecraft simply adds a small nudge in the direction it is already moving, stretching its orbit into a long ellipse that carries it out to the desired distance. The sun's gravity handles most of the actual geometry of the journey. A well-timed push is all that is required, and the natural shape of the resulting orbit does the rest. To travel upward, none of the existing momentum helps. Everything the spacecraft needs to do in the perpendicular direction must be paid for in full, with fuel burned in space, with no orbital shortcut available. The sun's gravity, always pointing inward toward the sun itself, offers no assistance with a climb that is aimed sideways relative to it. Every kilometer per second of vertical speed must be purchased outright. This is why, in the engineering sense, the polar regions of the sun are more remote than the outer planets, despite being no farther away in physical distance than any other part of the sun. The poles are hard not because they are distant, but because they exist in a direction that 4.5 billion years of orbital dynamics have made structurally expensive to reach. The solar system is generous to travelers moving within its disk and indifferent to travelers trying to leave it. There is no malice in this geometry. It is simply the patient consequence of how a solar system forms and what it holds on to. There is, fortunately, one elegant way around the delta V wall, and it is the technique that almost every ambitious deep space mission for the past 6 decades has relied upon. A spacecraft on precisely the right trajectory can swing past a planet and use that planet's gravity to redirect its path, gaining or losing speed relative to the sun without firing its engine at all. The planet, being incomparably more massive, gives up a microscopic fraction of its orbital energy in exchange. The energy is conserved. It simply moves from the planet's vast store into the spacecraft's comparatively tiny one. The maneuver is known as a gravity assist, a planetary flyby, or a swing-by, and it is very nearly the closest thing to something free that the physics of orbital mechanics offers. A single gravity assist can change a spacecraft's speed by several kilometers per second in a single encounter, depending on the mass of the planet involved, the relative speed of the flyby, and the precise geometry of the approach. More massive planets offer larger redirections. The angle at which the spacecraft skims past the planet determines whether the encounter adds speed, subtracts it, or bends the trajectory sideways. A careful trajectory designer can string together a sequence of precisely timed flybys to craft a path that pure rocket power could never afford. Jupiter, the solar system's largest and most massive planet, is also its most powerful natural slingshot. A carefully planned close flyby of Jupiter can shift a spacecraft's speed by 10 kilometers per second or more in a single pass. With the right approach geometry, Jupiter can throw a spacecraft cleanly out of the plane of the planets, bending its path sharply upward or downward relative to the ecliptic at essentially zero fuel cost. The fuel cost to the spacecraft, that is.
The mission design cost is substantial because the spacecraft must arrive at Jupiter at precisely the right moment, on precisely the right approach path, to achieve precisely the desired departure angle. Launch windows are narrow, and the trajectory, once committed, cannot easily be revised. Venus, smaller but much closer to Earth, can also be used as a lever, and used repeatedly. Each flyby of Venus adds a small amount of orbital inclination. Each pass tilts the spacecraft's orbit slightly more relative to the ecliptic. The process accumulates slowly, one nudge at a time, across many years and many passes. But patience, in this context, costs nothing in fuel. What would otherwise require an enormous delta-V budget instead requires years of mission lifetime, a trade that mission designers are often willing to make. Gravity assists do not bend any physical law. Energy is conserved in each encounter. Momentum is conserved. The spacecraft borrows from the planet's orbital motion, and the planet loses an immeasurably tiny amount as a result. Across many encounters, this borrowing is the difference between a mission that can reach the sun's polar regions and one that cannot. Almost every long-range exploration of the outer solar system has relied on at least one such assist along the way. In a very real sense, the technique is what makes serious solar system exploration possible at all.
There is a classical problem in orbital mechanics concerned with finding the most efficient path between 2 points in space within a given travel time. Within the plane of the planets, where everything is already moving in roughly the same direction at compatible speeds, elegant and practical solutions exist. Out of the plane, the problem becomes considerably harder because the connecting path must fight every convenient shortcut that orbital geometry normally offers. There is no need to dwell on the mathematical details. The essential point is only this. The universe makes it straightforward to move between bodies that share a plane, and considerably more difficult to connect bodies within the plane to points in the empty space above or below it. The disk rewards travelers who remain within it, and charges heavily for those who try to leave. This is the deeper reason that mission planners, when ranking potential destinations, consistently treat the polar regions of the Sun as more demanding than the distant icy bodies at the outer edge of the planetary system. Those icy bodies are, at least, in the disk. The poles of the Sun are not. The disk is generous to travelers moving within its flow, and frugal toward those attempting to cross it. Nothing in the universe forbids the crossing. The crossing simply costs more than the available rockets can deliver in any single straight ascent. Every spacecraft that has ever meaningfully climbed out of the plane has done so by using planets as a kind of staircase, trading time and geometric complexity for the missing delta-V. The history of solar system exploration is, in one reading, the history of working imaginatively around this single structural constraint. Missions to the inner planets ride the existing orbital currents with small adjustments. Missions to the outer planets ride those currents and borrow from Jupiter or Saturn along the way. Missions that aim to leave the plane entirely must combine both techniques and add patience on top. Every familiar mission profile carries embedded within it the fact that the solar system is flat, and that this flatness enforces itself upon every spacecraft we launch. Even the vocabulary of mission design reflects this. Spacecraft are described by their inclination capabilities, their delta-V budgets, their flyby sequences. The shape of a trajectory is named not only for where it is going, but for how it bends to get there, how it accumulates the changes of direction it requires. A mission to a planet on the disk is described straightforwardly. A mission to climb above the disk is described in nested layers, phase by phase, flyby by flyby, year by patient year of orbit shaping. The two kinds of missions do not exist in the same engineering universe. The current of the solar system is not precisely a prison. A current is perhaps a better word for it. One wide, flat, continuous sheet of motion circling the central star, having persisted for billions of years. Moving anywhere within that sheet is manageable. Moving out of it is not. The mathematics governing this are the same mathematics that govern every orbit, the same conservation of angular momentum that once flattened the protoplanetary cloud,
the same gentle physical laws operating at every scale. The geometry holds its shape with the patience of something very old, and it holds every spacecraft we launch within itself. Climbing out of it is not forbidden. It simply demands a different kind of mission than the ones that have so far defined our presence in space. Nearly everything humanity has ever learned about the sun has been learned while looking at its equator. The sunspot records, the flare observations, the tracking of magnetic features across the visible face, the bright streaming corona seen during total eclipses, the careful documentation of the 11-year cycle of solar activity. All of this is essentially equatorial science. The sun's poles, the two regions where its spin axis meets its outer atmosphere, are largely hidden from any observer remaining within the plane of the planets. Even at the most geometrically favorable moments, the poles appear foreshortened and compressed, flattened against the curved edge of the visible solar disk. Seeing them clearly requires a vantage point above or below the sun's equatorial plane, and such vantage points have been available for only the briefest intervals in the history of solar observation.
This matters considerably more than it might first seem, because the poles are not peripheral to how the sun behaves. They are not quiet corners or afterthoughts. They are among the most dynamically significant regions of the star. They are where the fastest component of the solar wind originates. They are where the global magnetic field undergoes its periodic reversal. They appear to be where the deep engine of the sun's long-term variability is housed. Much of what we observe happening at the equator, the sunspot cycles, the flares, the eruptions, is the visible downstream expression of processes that begin at the poles. To study only the equator is to watch a river's surface without ever asking where the current comes from. The idea that opens this part of our exploration is the coronal hole. A coronal hole is a region in the sun's outer atmosphere, the corona, where the magnetic field lines do not form the closed loops visible elsewhere on the sun, but instead extend outward, open, into space. Through these open regions, the hot ionized gas of the corona, called plasma, can stream outward freely along the open field lines, escaping rather than circling back to the surface. In ultraviolet images of the sun, coronal holes appear as dark patches, not because they are cooler in the dramatic sense, but simply because the plasma within them is less dense than the plasma in the surrounding closed-loop corona. During the quieter phases of the 11-year solar cycle, large, stable coronal holes settle into both polar regions of the sun, sometimes persisting for years with only gradual change. It is from these polar coronal holes that the fast solar wind originates. This stream of plasma exits the polar regions at roughly 700 to 800 kilometers per hour, nearly twice the speed of the slower wind that emerges from the sun's equatorial regions. The fast wind also carries a subtly different chemical signature, with element ratios and ionization states reflecting the different conditions in which it forms. The slower equatorial wind drifts outward at roughly 300 to 500 kilometers per hour, originating from the boundaries of coronal holes and from a region near the sun's middle called the streamer belt, where the magnetic field forms the bright looping arches visible during a total solar eclipse. The slow wind is more turbulent and more variable in density than its faster polar counterpart. Both types of wind coexist in the space around the planets, arriving in alternating streams as the sun rotates and presents different regions toward us in turn. Where the fast polar wind encounters the slower equatorial wind, the sun's magnetic field forms a thin, undulating boundary surface that spirals outward through the entire solar system, separating regions of opposite magnetic polarity. As the sun rotates, this surface rises and falls like the hem of a gently spinning skirt, sweeping past the planets in a slow, rhythmic pattern. The technical name for this structure is the heliospheric current sheet, the largest continuous magnetic structure in the solar system. It is often described as resembling a ballerina's skirt, and the comparison is apt. Earth crosses the heliospheric current sheet several times during each solar rotation. Each crossing produces small but measurable changes in the magnetic environment around our planet. The sheet is not visible to the eye. It is traced indirectly by spacecraft that pass through it and register the magnetic field's direction shifting as they cross the boundary. The amplitude of the ripples in the current sheet varies with the solar cycle.
wild and steep near solar maximum when the sun is most active, nearly flat along the solar equatorial plane near solar minimum. The shape of this great spiraling magnetic sheet, seen from directly above the sun, would be one of the more remarkable sights in the local solar system. A slowly rotating, gently warping surface of magnetic structure, stretching outward past the planets, undulating across the years with the sun's shifting mood. No true image of the current sheet has ever been assembled. Its shape is inferred from measurements taken by spacecraft crossing through it and from observations of the corona. A sustained view from above would reveal for the first time its actual three-dimensional geometry. Approximately every 11 years, the sun's magnetic field reverses polarity. What was the north magnetic pole becomes the south, and the south becomes the north. This is half of a full 22-year magnetic cycle, sometimes called the Hale cycle, and it appears to drive much of the solar activity we observe. The rise and fall of sunspot numbers, the size and shape of the polar coronal holes, the frequency and intensity of flares, and the overall structure of the corona. The reversal does not happen all at once. It is a process that unfolds across years.
The reversal originates at the poles. Throughout each 11-year phase, magnetic flux of the opposite polarity migrates slowly from active regions at lower solar latitudes toward the poles. Sunspots in active regions tend to come in pairs with opposite polarities, and one polarity of each pair reliably migrates poleward through diffusion and slow surface flows across the years. When enough of the new polarity has accumulated near a pole, it cancels the existing polar field, and the global orientation flips. The two poles do not always reverse simultaneously. One sometimes leads the other by months or even years, during which the sun briefly carries a more complicated magnetic structure than a simple two-pole configuration. Eventually, the second pole catches up, and the sun resettles into a clean dipole pointing the opposite direction from before. The complete transition from the beginning of flux migration to the final settling of the reversed field occupies most of the 11-year cycle. The strength of the polar magnetic field at the end of one cycle appears to forecast the intensity of the next cycle. A strong polar field is generally followed 11 years later by a vigorous sunspot cycle. A weak polar field tends to precede a quieter one. The relationship is not a rigid rule, and the precise mechanism is still being worked out, but the correlation is strong enough that polar field measurements serve as one of the more useful forecasts of coming solar behavior. In this sense, the poles function as the dynamo room of the sun, the place where the activity we observe at the equator finds its origin, and where the memory of one cycle is stored against the next. What limited imagery exists of the polar regions suggests that the surface texture near the poles differs from the equatorial surface. There are no large sunspot groups near the poles. Instead, the magnetic field appears to fragment into vast numbers of small, tangled concentrations woven through a fine network. The visible solar surface near the poles carries a different character than the familiar equatorial regions, smaller, less organized features, rather than the large active regions and sunspot groups that dominate the latitudes where most of the sun's familiar drama plays out. Extending outward from the polar regions, long, thin streams of plasma called polar plumes reach away from the surface like blades of grass aligned with the open magnetic field lines. The plumes are most easily seen during total solar eclipses, when the bright solar disk is briefly hidden and the faint corona can be studied. From within the plane of the planets, the plumes appear as faint rays curving away from the sun's polar edges. From directly above a pole, they would radiate outward in all directions along the open field lines, like the petals of a slowly spinning flower. Each plume is a narrow column of slightly denser plasma threading through the surrounding outward streaming fast wind. Imagining the sun from this vantage, not as a disk, but as a sphere seen from above its own axis of rotation, the familiar dark equatorial spots would be replaced by a quiet surface threaded through with delicate outward-reaching plumes. The magnetic field would be laid bare in a geometry that no equatorial view can fully reveal. There is something a little calming about this image of the sun, as something patient and geometrically precise, its poles streaming their quiet wind outward into the surrounding dark. The poles also carry the sun's longer-term magnetic memory. The reversal cycle does not proceed with identical intensity each time. Some cycles are stronger than others. There are even extended periods spanning centuries when the sun's activity drops substantially, with weak sunspot cycles and quieter magnetic behavior overall. These extended quiet phases appear to be connected to weaknesses in the polar field persisting across many successive cycles. The sun's variability over decades and centuries seems to trace back, like the cycle itself, to the slow accumulation and decay of magnetic flux at the poles. Even the geometry of large solar eruptions reflects the poles' influence. The enormous filaments and prominences that occasionally lift off from the sun's surface tend to align themselves with the boundaries between regions of opposite polarity. As magnetic flux migrates poleward through each cycle, these boundaries shift with latitude, and the locations of major eruptions drift accordingly. Charted over many cycles, this pattern produces the famous butterfly diagram of solar activity. Sunspot bands appearing first at high latitudes early in each cycle and migrating toward the equator as the cycle matures. All of it is the visible consequence of processes that begin at and return to the poles. The polar coronal holes themselves deserve a few more unhurried sentences. During the sun's quietest phases, a polar coronal hole can extend from the pole itself down to around 60 degrees of latitude, sometimes further. Its boundaries are irregular, wandering across the high latitudes with bays and peninsulas of open field intruding into the surrounding closed-loop corona. The overall shape shifts across weeks and months, but the existence of a large, stable polar hole during solar minimum is one of the most persistent features of the solar atmosphere. As the cycle progresses toward maximum, the holes shrink. The migration of opposite polarity flux, the increasing complexity of the lower latitude field, and the eventual reversal of the polar field all work together to break up the polar holes during the active phase. At solar maximum, they may be nearly absent, replaced by smaller, less organized coronal holes at various latitudes. After the reversal completes, the polar holes gradually rebuild themselves with the opposite polarity, growing back to their full extent as the next minimum approaches. The fast solar wind flowing from the polar holes carries a distinct elemental signature. The ratio of certain elements in the fast wind compared to the slow wind differs in ways that reflect the different conditions at each wind's origin. The slow wind, emerging from closed-loop corona at lower latitudes, carries a composition that has been chemically modified by extended confinement in the corona, with certain elements enriched. The fast wind, escaping more directly through the polar hole's open field lines, carries a composition closer to that of the photosphere beneath it. These compositional differences are measurable, and they help researchers trace any given sample of solar wind back to its likely origin region on the solar surface. At the microscopic level, the polar surface shows the same pattern of convection visible everywhere else on the sun. The granulation pattern, with hot plasma rising in bright cell centers and cooler plasma descending along darker edges. Above the granulation near the poles, the magnetic field threads upward in countless small bundles. These bundles organize themselves into the larger plume structures that radiate outward, and together form the texture of the polar corona, as seen during eclipses or from a spacecraft at high inclination. The poles also play a quieter role in the sun's differential rotation. Unlike a solid body, the sun's equator rotates faster than its poles, completing one rotation in about 25 days at the equator versus more than 30 days at high latitudes. This difference in rotation rates stretches the sun's magnetic field lines around it over each cycle, building up the twisted, complicated magnetic structures that eventually give rise to sunspots, flares, and the eventual reversal of the polar field. The poles, in setting one end of this differential rotation gradient, are indirectly responsible for winding up the very engine that drives the whole cycle.
Beneath the visible surface, the deep interior rotates with its own complex patterns, varying with both latitude and depth, and the boundaries between regions rotating at different rates are thought to be where the strongest field generation occurs.
The overall picture, then, is of a long chain of processes that begins deep in the solar interior, propagates through the convective layers, emerges at the surface as sunspots and active regions, migrates poleward across the years, and ultimately accumulates at the poles to produce the reversal that sets up the next cycle. The poles are both the end of that chain and its beginning, the place where the cycle's memory is deposited and held from one phase to the next. And yet, they have been studied, for the overwhelming majority of the history of solar physics, from an angle that makes proper observation almost impossible. The geometry of the disk has kept us at the equator, looking sideways at a star whose most important dynamics live at the top and the bottom. The sun has been turning, reversing, and streaming its polar wind for billions of years, with no one watching from the directions that would make the watching most illuminating. The two missions that have ever tried, in their different ways, to change that are the subject of what comes next. Only two spacecraft in the entire history of spaceflight have ever climbed meaningfully out of the ecliptic to observe the sun's poles from above. Both stories are worth dwelling on. Both are partial. The first reached genuinely high solar latitudes, but carried no camera capable of photographing the sun's surface directly. The second is currently in progress, climbing gradually out of the plane through repeated passes of an inner planet, and has very recently delivered the first close, direct images of one of the sun's poles ever obtained by any spacecraft. Between them, these two missions represent the full sum of human experience above the plane of the planets. Neither has been able to hold station above a pole. Both have been moving past on their inclined orbits, sampling briefly, then sweeping back through whatever portion of the disk their trajectories next carried them through. The first mission to climb above the ecliptic was a joint undertaking between a North American space agency and a European one, planned across many years and launched from low Earth orbit aboard a winged orbital vehicle. The spacecraft was compact for an interplanetary probe, with a large communication dish and a slowly spinning body designed to keep its instruments uniformly exposed to the sun. It carried tools for measuring magnetic fields, solar wind particles, energetic ions, dust, radio emissions, and cosmic ray populations at high latitudes. What it deliberately did not carry was a high-resolution telescope. No camera on board could photograph the sun's surface or its detailed coronal structure. The mission was designed to measure the high-latitude environment, not to image it. The path this spacecraft flew is among the most elegant pieces of trajectory design ever attempted. Rather than heading toward the sun, the spacecraft launched outward, toward Jupiter, on a long, looping path chosen with great care. It used Jupiter's enormous gravity in a precisely timed flyby to bend its orbit sharply out of the plane of the planets. After that encounter, the orbit was tilted by roughly 80 degrees relative to the ecliptic, almost perpendicular to everything else in the solar system. The spacecraft then began looping around the sun on this steeply tilted orbit, climbing high above the ecliptic at one end of each loop and diving deep below it at the other. The beauty of this maneuver is that it could not have been achieved with chemical propellant alone. The delta V required to tilt an orbit by 80 degrees through direct ascent from Earth would have been many tens of kilometers per second, far beyond what any chemical rocket has ever delivered to any spacecraft. By first making the long detour to Jupiter, the spacecraft obtained the inclination change essentially for free from the planet's gravity. The trip took years longer than any direct climb would have, but it accomplished something a direct climb could not have done at all. It was the first practical demonstration that the sun's polar regions, while structurally expensive, could actually be visited if the mission was clever enough with its use of available gravity. The scientific harvest from this first mission was substantial. It confirmed through direct, in-place measurement that the fast solar wind does indeed stream predominantly from the polar regions, while the slow wind originates at lower latitudes. Before this mission, the two-wind picture had been assembled from ground-based observation and theoretical modeling, without anyone ever having flown above the plane to verify it. The first mission flew through both polar regions and directly measured the wind speeds, compositions, and magnetic structures it encountered. The fast wind was there, precisely where the models had anticipated. The mission also confirmed the reality of the heliospheric current sheet's ballerina skirt geometry. As the spacecraft climbed to higher latitudes, it crossed the current sheet less frequently, exactly as expected if the sheet were a roughly equatorial structure, warping only modestly into higher latitudes. The sheet structure as a function of solar latitude and how it changed across a full solar cycle was mapped for the first time from a perspective that could see how it varied with height above the plane. One less expected finding from the first mission concerned the large-scale structure of the Sun's magnetic field at distance. Close to the polar surface, the field was as distinctly polar as models had suggested, with open field lines streaming outward from the coronal holes. But further out from the Sun, the field became surprisingly uniform across all latitudes. The radial component of the heliospheric magnetic field at sufficient distance was roughly the same in all directions, smoothed by the way solar wind plasma carries magnetic flux outward through space. The field structure, it emerged, was more local than expected near the surface and more global than expected at distance. The heliospheric magnetic field is organized somewhat differently at different scales.
The first mission also traveled through regions no spacecraft had previously visited. At high heliospheric latitudes, it measured cosmic ray populations, interstellar dust grains drifting in from outside the solar system, and energetic particles produced by solar activity, all in environments that had simply never been directly observed before. The cosmic ray data at high latitudes told astronomers something genuinely new about how galactic cosmic rays enter the heliosphere from above, a question impossible to address from inside the plane, where the geometry is different. The mission operated for nearly 2 decades before going silent. The orbit it traced continues to loop above and below the Sun, carrying the inert spacecraft along it. A permanent, if silent, monument to a trajectory nobody else has yet repeated. What the first mission could not do, for all its accomplishments, was produce an image. It could measure the wind and map the magnetic field. It could not photograph the polar surface from above. The actual visual character of the polar regions of the Sun, the appearance of the surface and the corona at those latitudes, remained essentially unknown when the mission ended. The closest thing to a polar image that existed before recently was a foreshortened glimpse from inside the ecliptic, with the pole tilted toward the observer at a shallow angle and most of the detail compressed and lost in projection. Decades later, a European-led mission took a different strategic approach. Rather than using Jupiter to achieve a large, single inclination change, this newer spacecraft uses repeated flybys of Venus to tilt its orbit gradually, a small increment at a time. Each pass of Venus adds a few degrees of orbital inclination. The process is slow, but over many years and many flybys, the spacecraft climbs steadily out of the plane, reaching higher solar latitudes with each successive loop. Patience costs nothing in Delta V.
The newer spacecraft carries a comprehensive imaging suite, deliberately complementing what the first mission lacked. A high-resolution telescope images the solar surface in visible light. A magnetograph measures the surface magnetic field directly, latitude by latitude. Ultraviolet imagers capture the corona at the wavelengths where hot plasma glows most brightly. Coronagraphs image the extended corona by blocking the bright solar disk. In situ instruments measure the local wind and magnetic environment around the spacecraft itself. The mission is, in effect, a portable solar observatory designed to apply to the polar regions the same quality of study that equatorial regions have received for decades. The spacecraft's orbit carries it relatively close to the Sun at its nearest point. Thermal management is a core design challenge. A specialized heat shield protects the instruments from the intense sunlight at close approach.
Small doors in the shield can open briefly when the spacecraft is far enough from the sun for the optics to operate safely. The engineering is demanding, but demonstrably workable, as multiple close approaches have now confirmed. As of recently, the spacecraft has begun reaching the orbital inclinations needed to actually see the polar regions. The first direct, close-range images of one of the sun's poles have now been returned. What those images showed was not the familiar equatorial face of the sun. The surface texture in the polar images was finer and more chaotic. The magnetic field appeared less organized, threading through countless small concentrations rather than gathering into the broad active regions that characterize lower latitudes. The polar plumes were resolved as individual rays of plasma extending outward from the polar coronal hole, with a gentle lune reflecting the curvature of the rotating magnetic field. It was the first time human eyes had seen the sun from this direction at any meaningful resolution. There is no archive footage from before this moment. The record simply did not exist.
The two missions together have established what neither could have demonstrated alone. The first proved that the polar regions behave differently from the equator. Different wind speed, different field structure, different particle environment. The current mission is now supplying what the first could not: imagery, magnetic maps, ultraviolet corona structure, and the visual appearance of the polar surface itself. Between them, they have shown that a vantage point above the ecliptic is not a luxury for solar physics. It is a requirement for understanding the sun as the three-dimensional, actively cycling object it actually is, rather than as the flat disk it appears to be in every equatorial photograph. And yet, even with both missions' contributions combined, only a small fraction of what a dedicated polar observatory could provide has been obtained. Neither mission has been able to remain above a pole for long. Both have been passing through, sampling the high latitudes during the intervals when their orbits carried them there, then sweeping back toward lower latitudes as each loop continued. A spacecraft able to simply sit above a pole for years, observing continuously while the sun rotated beneath it, has not yet been built. The full polar picture of the sun, the one only sustained continuous observation from a true polar vantage could assemble, is still waiting to be written. The progress so far, compared to the long years of having no polar observations at all, is very large. The remaining gap, compared to what sustained polar observation could eventually provide, is also very large. Both things are quietly true. The poles have been visited briefly. They have not yet been lived with. The instruments aboard each of these two missions deserve a closer consideration because instruments define the shape of what any mission can learn. The first mission carried tools for characterizing the physical conditions of the high-latitude heliosphere, the strength and direction of the local magnetic field, the density and speed of solar wind particles, the composition of energetic ions, the population of cosmic rays at high latitudes, the radio signals produced by various plasma processes, and the characteristics of dust grains passing through interplanetary space. Each measurement type required a different instrument tuned to a specific kind of particle, wave, or field. The spacecraft was, in essence, a portable physics laboratory being transported to places no laboratory had previously been. The magnetic field sensor on the first mission was a fluxgate magnetometer, a device that measures the strength and direction of a local field with high precision. It was mounted on a long boom extending from the spacecraft's body, keeping it away from any interference from the spacecraft's own electronics. The boom was deployed shortly after launch and remained extended throughout the mission, the magnetometer at its tip taking continuous measurements as the spacecraft moved through the heliosphere at various latitudes. The resulting record is one of the most detailed continuous accounts of heliospheric magnetic structure ever assembled across a wide range of solar latitudes. The particle detecting instruments on the first mission covered a wide range of energies, from the relatively cool plasma of the solar wind itself through the more energetic particles accelerated by solar flares and interplanetary shocks, all the way to the extremely energetic cosmic rays arriving from well outside the heliosphere.
The detectors counted particles, measured their energies, and in some cases identified their atomic species. The combined data provided the first comprehensive portrait of the particle environment at high heliospheric latitudes, across a range of energies and across more than one full solar cycle.
The dust detector was a piezoelectric sensor designed to register the tiny impacts of individual dust grains striking the spacecraft. Each impact produced a small electrical signal, the amplitude of which related to the grain's mass. By counting impacts and analyzing their characteristics, the instrument assembled a picture of the dust environment at latitudes well above the ecliptic, a region where the dust population had never been directly measured. Among the results was evidence of interstellar dust grains drifting into the solar system from outside, distinguished from local solar system dust by their motion and composition. The radio and plasma wave instrument detected the low-frequency electromagnetic waves and plasma oscillations that permeate the heliosphere, carrying information about solar flare disturbances, interactions between the solar wind and the heliospheric boundary, and other large-scale processes. The instrument registered, among other things, radio signatures of shock fronts propagating outward through the system, and on occasion, signals from the distant boundary region where the solar wind encounters the surrounding interstellar gas. The current mission's instruments were assembled with a deliberately different philosophy. They retain the in-situ physical measurement capability of the first mission while adding the imaging suite that the first mission lacked. The Visible Light Telescope can resolve features on the solar surface at scales of a few hundred kilometers, comparable to the finest detail available from ground-based telescopes during the best seeing conditions. The magnetograph produces direct maps of the surface magnetic field, showing at a glance the strength and orientation of the field across the visible solar disk. The ultraviolet cameras capture the corona in the wavelengths where its hot plasma radiates most strongly, revealing magnetic loop structures, active region boundaries, and coronal hole edges. The coronagraphs use small occulting disks to block out the bright photosphere, imaging the faint extended corona continuously, the same technique that produces dramatic eclipse corona images, but operational at any time rather than only during rare eclipses. The combination of magnetograph, ultraviolet images, and coronagraphs gives the current mission a layered, simultaneous view of the Sun, from the visible surface upward, through the chromosphere, and into the extended corona, all from one spacecraft. When the orbit reaches the inclinations where polar regions come into view, all these instruments are directed at the new vantage. Polar surface, polar magnetic field, polar corona, and local plasma environment are measured together in the same coordinated way that equatorial regions have been studied for decades. A polar science archive is beginning to accumulate, modest in volume compared to the equatorial record built across a century of solar observation, but comparable in kind. Frame by frame, measurement by measurement, the picture of the Sun as a three-dimensional object is slowly being assembled. The work is patient, the data is sparse, the picture is still very much unfinished. The Sun's influence does not end at the orbits of the planets. The solar wind continues outward, gradually thinning with distance, carrying the Sun's magnetic field with it across distances far greater than the planetary system. Eventually, the outward-flowing wind encounters the surrounding gas and dust of the local interstellar medium, where the pressures of the two environments balance and a boundary forms. The enclosed region, the great bubble of solar plasma carved out by the Sun's wind, is called the heliosphere. Its outer boundary is the heliopause. Everything we think of as our solar system, the planets, the asteroid belt, the Kuiper belt, the inner reaches of the distant comet cloud, all exist deep inside this bubble. The heliosphere is our local magnetic environment, our local weather system, our shield against the somewhat harsher conditions of the interstellar medium beyond it. The shape of the heliosphere is one of the open questions in contemporary astronomy, and as with so much else in tonight's exploration, the difficulty in answering that question comes back to the fact that everything we have measured of the heliosphere has been measured from within the plane of the planets, from inside the disk that the entire solar system shares. The bubble that contains us has never been observed from outside.
It has never been imaged in a plan view. It has never been mapped from any vantage that does not itself sit within the flat geometry the bubble defines.
For decades, the standard mental picture of the heliosphere was the shape of a comet. The Sun moves through the surrounding interstellar gas at about 26 kilometers per second relative to that gas. This motion was thought to compress the heliosphere into a rounded leading surface on the upwind side, where the Sun pushes into the gas ahead of it, and to stretch the bubble into a long tapering tail on the downwind side, like a comet trailing behind itself through its own atmosphere. The picture was inferred from how the solar wind should theoretically interact with the interstellar gas, and it was supported by observations of somewhat similar bubble structures around other moving stars elsewhere in the galaxy. The comet picture fit much of the available data, made specific predictions about the boundary's location and structure, and served as the working model for most of the late 20th century and into the early 21st. Two distant spacecraft, launched generations ago and still traveling outward, have crossed the heliosphere's boundary into interstellar space. Their measurements offer the closest thing we have to direct observations of the heliopause. Both spacecraft, however, crossed near the upwind nose of the bubble, and both did so roughly within the plane of the planets. They could not observe the tail. They could not measure the structure above or below. They sampled only the fraction of the boundary that happened to lie along their own trajectories. What they found was richer and stranger than the simplest comet-shaped models had anticipated. A more recent model, developed by researchers studying how the heliosphere interacts with the surrounding interstellar magnetic field, proposes quite a different shape. Rather than a long downwind tail, this model suggests the heliosphere resembles a deflated shell with two curved lobes extending back from the upwind nose, separated by a narrow waist, with no extended tail at all. In this picture, the Sun's magnetic field, carried outward through the solar wind, is strong enough at the boundary to pinch the bubble closed on the downwind side, preventing the long tail that the comet picture assumed. The bubble in this model is more compact, and its geometry is closer to a curved shell than a flowing teardrop. This alternative shape is consistent with some measurements taken inside the heliosphere, including maps of energetic neutral atoms, particles that travel inward from the boundary and can be detected without flying out to it. The model also predicts a closer downwind boundary than the comet picture implied, with the heliosphere perhaps not extending much further behind the Sun than it does in front. The debate continues. The data is sparse. The geometry is genuinely hard to reconstruct from measurements taken only from within the plane. The truth may lie between the two pictures, or in some configuration neither has yet proposed. There is something that feels quietly humbling in the recognition that no spacecraft, no telescope, no instrument of any kind has ever observed the heliosphere from outside its own plane. Our solar system has been mapped with increasing precision for centuries. The soft boundary separating the Sun's influence from the interstellar wind beyond it has never been drawn from direct observation. We are still waiting for the first portrait of our own local bubble, the first image from outside the shape we live inside. To address some of these questions without waiting for a spacecraft capable of leaving the plane, a planned interstellar mapping mission is being prepared. This probe, designed to orbit relatively close to Earth, will measure energetic neutral atoms streaming inward from the heliospheric boundary across the full sky. By recording the directions and energies of these inward traveling particles, the mission can infer the three-dimensional shape of the boundary without ever traveling to it. The reconstruction would be indirect, but informative, refining our picture of the bubble from the inside even without the outside vantage point. Energetic neutral atoms form when charged solar wind particles streaming outward encounter neutral atoms drifting inward from the interstellar medium. The interaction can transfer an electron from the inward particle to the outward one, producing a fast neutral particle that is no longer bound to the magnetic field and can travel in a straight line back through the heliosphere toward the inner solar system. The arriving neutrals carry information about where the exchange occurred, and thus about the structure of the boundary region itself. Detecting them from many directions simultaneously builds a kind of spherical map of the distant boundary. The technique is not unlike how certain medical imaging methods reconstruct internal structures from particles arriving at different angles without the detector needing to be inside the structure. An earlier in-plane mission used a lower sensitivity version of this approach and produced the first all-sky maps of the heliospheric boundary, revealing an unexpected feature: a bright ribbon of enhanced neutral atom emission arcing across the sky in a particular geometric pattern. The ribbon's precise origin is still being worked out, but its existence demonstrated that the boundary region carries more structure than the simplest models had imagined. The new mission will map it at significantly higher resolution, improving the chances of distinguishing between the competing models of the heliosphere's overall shape. The neutral atom approach, however, is inherently indirect. It maps the bubble's boundary through inference rather than direct measurement. A spacecraft climbing above the ecliptic could measure the boundary directly, observe the high-latitude magnetic structure, and, given enough altitude and patience, potentially cross the heliopause in a direction perpendicular to the disk, returning the first observations ever made of the heliospheric boundary from above or below. No such mission currently has funding. The architecture has been worked out. The spacecraft has not been built. The heliosphere itself is not a static structure. It breathes with the solar cycle. As the sun's activity rises and falls across each 11-year period, the solar wind's pressure changes and the bubble responds. During solar maximum, when the wind is more intense, the bubble pushes outward and the boundary moves further from the sun. During solar minimum, it retreats inward. The two spacecraft that have crossed the boundary did so at different phases of the solar cycle, and the boundary distances they measured reflect the cycle's state at those moments. The interstellar medium surrounding our bubble is also not uniform. The Sun is currently drifting through a relatively low-density region of interstellar gas called the local interstellar cloud, which is itself embedded within a somewhat larger and even emptier region called the local bubble, a cavity thought to have been carved by supernova explosions several tens of millions of years ago. The boundary of our heliosphere therefore sits inside a bubble within a bubble, the inner one maintained by the sun's wind, the outer one made by the deep past explosions of nearby massive stars. When the sun eventually drifts out of the local interstellar cloud and into a different region of the interstellar medium, the conditions at the heliopause will change. A denser surrounding environment would compress our bubble inward. A thinner one would allow it to expand. The boundary is not a fixed wall. It is a balance, and the balance shifts as the surrounding pressures shift. The current size of the heliosphere reflects the current external conditions, and it has been roughly its present size for most of recent solar history, modulated by the slow rhythm of the cycle. The orientation of the interstellar magnetic field also shapes the heliosphere's structure. The field threading through the local interstellar gas exerts a real pressure on the boundary, influencing its shape in ways that models without magnetic fields cannot fully capture. Distinguishing the magnetic field's contribution from that of the gas pressure itself requires measurements at or very near the boundary, and such measurements come from only two trajectories, both in roughly the same direction. Beyond the heliopause lies the interstellar medium proper: low-density hydrogen gas, a scattering of dust grains, magnetic fields, and the population of energetic cosmic ray particles that fill the galaxy. The two spacecraft now sampling this environment from just beyond the boundary are returning at very low data rates, the first in-situ measurements ever made of the space between the stars as it actually exists near our own solar system.
Further still, the sun is moving through the galaxy in a long, slow drift that has carried it through many different environments across its history. Dense molecular clouds, quiet interarm regions, the brighter and more active spiral arms. Each passage has been accompanied by a changing heliosphere, compressed or expanded according to the density of the surroundings. The heliosphere we know today is simply the most recent in a long sequence of heliospheres, each shaped by the conditions of its era. There is something quietly grounding in the full picture of where we are, considered gently. A planet orbiting a star, inside a bubble of solar wind,
inside a region of low-density interstellar gas, inside a larger cavity carved by ancient stellar explosions, inside a spiral arm of the Milky Way, inside the disk of the galaxy, inside the small cluster of galaxies of which the Milky Way is the largest member, inside the much vaster volume of the observable universe. Each layer wraps the next. Each carries its own shape, its own history, its own physics. Tonight's central question, what sits above and below the sun, is in part a question about how clearly we can see those nested layers from where we actually are. From inside the plane, we observe them through the disk that contains us. From above the plane, we would observe them through considerably less. The portrait of our home is incomplete, not because the universe is inaccessibly far away, but because we have observed it from essentially one direction. The view from above or below has been available in principle since the first protoplanetary cloud collapsed. It has been available to instruments for only the briefest, most partial intervals. The full picture is waiting, as it has been for a long time, and the next part of tonight explores what it would actually take to go look. There is a way to escape the plane of the planets that does not require 30 kilometers per second of raw delta V from low Earth orbit. The approach is, of all things, to fall closer to the sun first, and only then to push. It is one of the most beautiful principles in spaceflight, understood since the earliest era of theoretical rocket science, yet counterintuitive enough on first encounter that it is worth explaining carefully. Once it has settled in, it carries a quality of quiet inevitability, like a piece of geometry that could not have been other than it is.
A spacecraft that burns its engine deep in a gravitational well, close to a massive body, extracts considerably more energy from the same burn than it would at greater distance. The reason is that the spacecraft is already moving very fast at the bottom of the well, and the kinetic energy a body possesses scales with the square of its speed. Adding a small velocity increment to an object already moving quickly produces a far greater change in total energy than the same increment added to something moving slowly. The fuel performs the same chemical work in either case. The engine produces the same thrust. What differs is the speed at which the burn occurs, and that speed multiplies the energy harvest through the squaring relationship that governs kinetic energy. A kilogram of propellant burned at 100 kilometers per second changes a spacecraft's energy budget enormously more than the same kilogram burned at 10 kilometers per second, even though the thrust produced is identical. This principle, sometimes called the deep well burn or the perihelion maneuver, was formalized in the early decades of theoretical astronautics by foundational work that underlies much of what we understand about orbital mechanics. Its practical consequences are everywhere in spaceflight. When a spacecraft arrives at a planet and wants to enter orbit, the engine burn is timed to coincide with the closest point of approach, the moment when the spacecraft is moving fastest, precisely because that is where the burn accomplishes the most useful work per unit of fuel. When a spacecraft wants to depart a planet on a long outward journey, the burn is again performed at the closest point for the same reason. The deep well principle is standard practice around any gravitating body. The reason this matters for tonight is that the sun is the deepest gravitational well in the solar system, and a burn near the sun extracts more energy than a burn anywhere else. Apply the principle to the sun, and the result is one of the most striking and most elegant maneuvers in proposed spaceflight. A spacecraft launched from Earth falls inward toward the sun. Gravity accelerates it enormously as it descends, to well over 100 kilometers per second at the closest point of its approach. At that perihelion, deep in the sun's gravitational well, the moment of greatest speed and greatest opportunity, the spacecraft fires its engine briefly. Because of the deep well effect, the small quantity of fuel burned at that velocity produces a vastly greater change in orbital energy than the same burn would produce from Earth's distance. The spacecraft then rises outward again, but now on a fundamentally different orbit, one that can carry it out of the plane of the planets entirely on a trajectory that would otherwise have required an impossible expenditure of fuel. The savings the maneuver provides are not modest. They are dramatic. A trajectory that by direct ascent from Earth would cost roughly 30 kilometers per second of perpendicular delta V can instead be accomplished for perhaps 3 or 4 kilometers per second, applied briefly at the right moment and in the right direction near the sun.
The geometry once again rewards working with the gravitational landscape rather than against it. The practical constraint is that the spacecraft must survive the thermal environment near the Sun, which is the central engineering challenge of the entire approach. At perihelion, the spacecraft is bathed in solar radiation of an intensity that can damage any conventional structure. The sunward surface temperature rises rapidly as the spacecraft falls inward. A specialized heat shield, of the kind already demonstrated in successful operation by certain modern solar probes, is required to protect the spacecraft through the critical interval of the perihelion burn. The thermal engineering is demanding. It is also clearly achievable. The demonstration has been made.
The maneuver additionally requires the spacecraft to arrive at perihelion still carrying nearly all of its fuel. Any propellant burned earlier in the trajectory forgoes the deep well amplification. The most efficient version of the approach saves essentially all available fuel for the brief perihelion moment and lets the Sun's gravity provide the inward acceleration for free. The spacecraft needs only to begin its fall with the right initial conditions. The geometry of the descent does the rest. This is among the cleanest examples in spaceflight of letting the gravitational landscape accomplish most of the work, using the engine only at the moment when its effect is most amplified. Picture the trajectory in quiet stages. The spacecraft departs Earth and curves inward, gathering speed as the Sun's gravity draws it down. The heat shield brightens. The Sun fills a larger and larger field of view, larger than any spacecraft has seen it from before. At perihelion, the moment of both greatest peril and greatest physical opportunity, the engine fires for only a few minutes. A brief burn is sufficient because the geometry at that moment is so favorable that a small push redirects the trajectory dramatically. The spacecraft then begins rising again, but rising now along a path that no direct descent from Earth could have produced, climbing steadily toward the solar polar regions on an orbit bought not with enormous quantities of fuel, but with patience and careful positioning.
There is another way out of the plane, and this one carries no fuel at all. A solar sail is an enormous, thin, reflective surface that catches the gentle but continuous pressure of sunlight. Every photon that strikes the sail and reflects away imparts a tiny amount of momentum to the craft. The impulse of any single photon is vanishingly small, but integrated across a sail surface measured in thousands of square meters and accumulated across months and years of continuous exposure, the total momentum transferred becomes significant. A sailcraft can change its orbit meaningfully without burning any propellant, simply by orienting its sail to use sunlight pressure the way a sailing vessel uses wind. Tilting the sail at different angles relative to the Sun allows the spacecraft to add energy to its orbit, subtract it, or gradually tilt the orbit's plane. The available thrust directions are more constrained than those available to a rocket engine because the thrust depends on where the Sun is and how the sail is facing. But within those constraints, a sail can execute maneuvers that no chemical mission could afford, simply by letting a small, continuous force accumulate across time. Practical solar sails for meaningful interplanetary maneuvering need surface areas in the thousands of square meters. The sail material itself must be extraordinarily thin, films just a few microns thick, folded compactly for launch and deployed in space through carefully engineered mechanisms. Small-scale sail technology has been demonstrated on experimental missions, and the engineering is well within current capabilities. What has been absent is the funding and collective will to build a sailcraft at the scale required for a serious solar-polar mission. Concepts for sail-driven polar solar missions have been studied under various forms for decades. A solar-polar imaging mission, in which a sailcraft spirals inward and raises its orbital inclination gradually through continuous sunlight pressure, has been a long-standing proposal in solar physics. Similar mission architectures have been worked out in considerable detail under different program names. Both approaches would use the patient, steady force of sunlight to accomplish what a chemical rocket could not afford in delta-v terms. Neither has been built. The fundamental advantage of the sailcraft is that it does not run out of fuel. As long as sunlight falls on the sail, the thrust continues.
Mission lifetime is limited by the sail material's durability and the spacecraft's electronics, not by a finite propellant supply. A sail-driven mission to the solar poles could, in principle, climb to a high-inclination orbit, observe across multiple years, and continue maneuvering as needed throughout its operational life. The economic implications of fuel-free maneuvering across such a mission duration are genuinely significant. The corresponding limitation is that sail thrust is gentle. The trajectory to the sun's poles via solar sailing takes considerably longer than a perihelion burn approach. The orbit shapes itself slowly, one small increment of inclination at a time. A mission patient enough to accept a multi-year spiral can reach destinations no chemical mission could afford. But the passage of time is real, and it matters for mission planning.
The most promising recent concepts combine both techniques. A sailcraft deploys from Earth and uses sunlight pressure to spiral inward toward the sun without consuming any propellant. As it approaches perihelion, the sail is furled or released, and a small high-energy propulsion stage performs the perihelion burn at closest approach. The trajectory that results climbs steeply out of the plane and into a polar orbit around the sun. The combined architecture trades the complexity of managing two propulsion systems and the careful handoff between them for a dramatic reduction in the total delta-V cost compared to either approach used alone. The sail handles the slow, patient work of getting the spacecraft into position near the sun. The perihelion burn handles the brief, decisive work of throwing it out of the plane. The result is more capable than either technique would be individually, in the way that good engineering often finds the whole exceeding the sum of its parts. Variants of this combined approach have been studied for decades, proposed, refined, modeled, and set aside repeatedly while waiting for the right alignment of scientific priority, funding availability, and political will. None has yet been assembled into a flying vehicle. The concepts remain on the longer list of beautiful and well-reasoned ideas in spaceflight that have been carefully worked out on paper and never yet built. Other propulsion approaches could also support out-of-plane missions, given sufficient development. Ion engines, which use electrical power to accelerate ionized propellant to exhaust speeds far beyond what chemistry can achieve, are considerably more efficient than chemical rockets in terms of delta-V per kilogram of fuel. Several interplanetary missions have already used them to perform maneuvers beyond the reach of chemical propulsion. An ion-driven spacecraft, given enough power and enough time, could in principle accomplish the gradual inclination changes needed to climb above the plane without a planetary flyby or a perihelion burn. The thrust is small, but it is continuous, and continuous thrust applied over years can accumulate into very large total velocity changes. Nuclear electric propulsion, using a small nuclear power source to supply electricity for highly efficient electric thrusters, could offer even more capable out-of-plane missions. A nuclear power source produces far more electricity than solar panels can at the distances from the sun where sunlight is dim. With sufficient power and patience, a nuclear electric spacecraft could climb out of the plane, hold position above a pole for years, and maneuver freely throughout the mission. The technology has been studied in detail. It has not flown at the scale such a mission would need. The choice among these architectures, when a polar solar mission eventually reaches the stage of serious development, will depend on cost, schedule, scientific priorities, and political circumstances. The purpose of this part of tonight's exploration is not to argue for any one approach. It is only to make something clear. The missions are possible. The geometry of the solar system is not an absolute barrier. The delta-V wall can be climbed through gravity assists, through the deep well perihelion maneuver, through the long patience of solar sailing, through the steady efficiency of ion propulsion, or through some combination of these. The polar regions of the sun are not truly beyond reach. They are beyond the reach of the kinds of missions we have so far built and launched. The principle of falling first in order to climb afterward is the unifying insight of this part. It is a reminder that the universe tends to reward those who work with the gravitational landscape rather than against it. The same principle that once flattened the protoplanetary cloud, that keeps the planets in their orbits, and that catches every spacecraft in the sideways current of the ecliptic, that same principle also offers the path out of that current for those patient enough to find the right place and the right moment to push. The deep well is not only the constraint, it is also the lever.
Pressed at the right moment, in the right direction, with the right preparation, the sun's own gravity can send a spacecraft to a vantage point that no amount of direct force could ever purchase.
Suppose, for the length of tonight's final part, that such a mission has been built. The architecture has been chosen, the spacecraft assembled, the trajectory flown. The spacecraft has arrived at a stable, patient orbit above the sun's north pole, or perhaps below its south, at a comfortable distance, far enough for the instruments to look freely, close enough for a stable communication link with home. The mission has begun. What does the spacecraft see? The first change is the sky itself. From inside the ecliptic, the night sky is faintly washed by the zodiacal glow, sunlight scattered by the plane's disk of dust into every equatorial line of sight. The glow is soft, but it is persistent, and it limits how faint an object can be before its light is lost against the background. From above the plane, that glow lies behind and below the spacecraft. It no longer scatters into the upward field of view. The sky overhead would be quieter and darker than any view available from within the solar system. Faint stars, distant galaxies, the cosmic microwave background, all would stand against a significantly cleaner backdrop. The implications for observational astronomy from such a vantage would be real and broad. Telescopes searching for signs of life in the atmospheres of distant exoplanets are limited, from Earth and low Earth orbit, by scattered zodiacal light forming an unavoidable bright background that competes with the extremely faint signal from a planet's atmospheric chemistry. A telescope operating from a polar vantage would look out through one of the clearest windows in the inner solar system, with that contamination substantially reduced. The faintest signals from distant planetary atmospheres would become more accessible. Measurements of the cosmic microwave background, the faint thermal relic of the universe's earliest moments, are similarly affected by foreground emission from the solar system's own dust. A polar vantage would reduce that foreground meaningfully, allowing more precise maps of the microwave background's small temperature variations. Those variations carry information about the conditions of the universe when the first hydrogen atoms formed, and the precision with which they can be mapped shapes how confidently we can reconstruct the universe's history. Even ordinary variable star monitoring, pulsar timing, and the long-duration observation of faint sources would benefit from the darker, cleaner sky at such a vantage. The Polar Observatory is not only a solar physics platform, it is a uniquely quiet window on the rest of the universe. The local environment around the spacecraft itself would also shift as it climbed above the plane. Near the solar equator, a spacecraft sits inside the relatively slow, turbulent, variable wind of the streamer belt. Slow plasma rising from boundaries of equatorial magnetic structures, threaded with the rippling current sheet, variable in density and direction from hour to hour. Climbing to higher solar latitudes, the environment changes. The plasma becomes faster, smoother, and more uniform. The straight streaming fast wind from the polar coronal hole, carrying less of the turbulence and variability that characterize the equatorial wind. The transition between the two regimes is gradual, spread across a range of latitudes, with mixed regions where fast and slow wind interact, and compression fronts form where faster plasma catches up to slower plasma ahead of it. The first polar mission traced these transitions at low resolution and found structures not fully anticipated by the simplest models. A sustained polar mission could map them in far greater detail. The cosmic ray environment also varies with latitude. Galactic cosmic rays, extremely energetic particles arriving from interstellar space, are partially deflected by the heliospheric magnetic field as they travel inward through the system. How effectively they are deflected depends on the geometry of the magnetic field, which itself varies with solar latitude in ways that have never been fully characterized from in-plane measurements. A polar spacecraft monitoring cosmic ray fluxes across many years would help clarify how the heliosphere modulates the galactic particle background, a question that touches on everything from the biology of ancient life on Earth to the shielding conditions experienced by any future travelers in the outer solar system. The magnetic field measurements at high latitudes would directly test the surprisingly uniform large-scale structure that earlier measurements had hinted at, the property by which the radial component of the heliospheric magnetic field becomes roughly equal in all directions once sufficiently far from the Sun. A sustained polar mission, measuring the field continuously across years and across different phases of the solar cycle, could establish precisely how that uniformity arises and how it evolves. The field's geometry is one of the more elegant unsolved problems in heliospheric physics, and the polar vantage is the natural place from which to study it. Turning the spacecraft's instruments downward, toward the plane of the planets, would produce another first. The disk of the solar system would be visible for the first time in history in plan view. The orbits of the planets, ordinarily mapped by inference from in-plane observations, would be laid out below the spacecraft in a single glance. The dust bands of the inner system, the asteroid belt, the paths of comets, all would form a great flat sheet below, illuminated by the sun beyond them. The geometry of where we live would, for the first time, be visible directly rather than inferred. Earth and the inner planets would appear as small bright points moving slowly along their paths. The whole inner system would fit within a single field of view. The spacing between orbits, the relative speeds, the slight inclination differences that distinguish one orbit from another, all would be directly resolvable in a way that is simply impossible from any vantage within the plane. The asteroid belt would show as a faint ring between the orbits of Mars and Jupiter, its internal structure, the gaps caused by resonant interaction with Jupiter, the larger Trojan populations sharing Jupiter's orbit, visible at a glance. Dust contributions from short-period comets and Kuiper belt objects would stand out more clearly against the darker background available from above the disk, allowing the various sources to be more precisely distinguished.
This image does not exist. It has never been taken. It cannot be taken from within the plane, because the geometry of the plane makes the plane itself invisible as a plan view. Only a vantage above or below the disk can capture the disk as a full, flat, spread-out thing. No spacecraft has ever held such a vantage long enough to make the image. The first plan view portrait of our solar system as a flat object, seen from the outside of its own flatness, is one of the great unfinished pictures in all of astronomy. With a long-lived mission and sufficient out-of-plane travel, the spacecraft could also begin to answer the open question of the heliosphere's shape. Direct measurements of the magnetic field and plasma at high latitudes, taken at various distances from the Sun, would distinguish between the comet-shaped model and the more compact alternative. The two models predict different configurations for the boundary, different distributions of magnetic structure at high latitudes, and different situations on the downwind side. A polar spacecraft sampling these properties at systematically increasing distances would determine which geometry is closer to reality. If the mission eventually crossed the heliopause from above or below at any distance from the upwind nose, it would return the first measurements ever made of the boundary in a direction entirely outside the disk. Such a crossing would extend the in situ map of the boundary into directions that have never been sampled from any trajectory ever flown. Either result, confirming the comet shape or the compact alternative, would substantially change our understanding of the structure of our local bubble. Look further outward from the polar vantage, and the galactic sky arranges itself differently than it does from Earth. The band of the Milky Way, tilted by roughly 60 degrees relative to the ecliptic, would no longer cut across the sky in the familiar arc. It would rise as a great slanting band, the bright galactic center lying in a different direction relative to the surroundings than it does from inside the plane. The constellations of the southern sky, the dark dust lanes threading through the stellar band, the soft glow of the galactic interior, all would present a different geometric arrangement, one that feels unfamiliar in a way that is hard to fully imagine until one is actually somewhere unfamiliar enough to see it.
The direction below the Sun's south pole opens into one of the clearer sight lines through the local bubble, the low-density interstellar cavity surrounding the Sun. From this direction, the interstellar foreground is thinner, the obscuring dust somewhat less dense. A telescope pointed in this direction from below the Sun would have a particularly unobstructed view outward into the wider galaxy. The geometry of the local bubble itself, the elongated cavity carved by ancient supernova explosions, with chimneys extending vertically out of the galactic disk, and a more complicated structure within the plane, would be more directly accessible from this vantage than from inside the plane. The cosmic microwave background would also be measurable from a cleaner position. Foreground emission from the galaxy and from the solar system's own dust makes it harder to measure with full precision from inside the disk. A polar vantage would reduce the solar system foreground substantially, leaving a cleaner residual signal. The temperature variations of the microwave background, its polarization structure, and the imprints left on it by large-scale structure in the early universe would all become slightly more precisely measurable. Even ordinary stars seen from above the plane would stand against a somewhat darker background. Faint stellar companions, faint exoplanets reflecting their parent star's light, and faint brown dwarfs drifting at the edges of nearby stellar systems would all be marginally easier to detect. The polar vantage is, in this sense, a modest but real improvement to nearly every kind of astronomy that depends on seeing faint sources against a background of unwanted light. No photograph of the solar system from outside its own plane exists. No image of the Sun taken directly from above one of its poles at full resolution in calm conditions for long enough to study the dynamics in real time has ever been made. These pictures do not exist yet. The engineering required to produce them is real and understood. The underlying physics is well established. The trajectories needed have been calculated in detail. We simply have not yet built the mission. The view above the Sun is one of the most consequential vantage points in the local solar system, and it remains empty, waiting for a spacecraft that has not yet been assembled.
Every direction we have ever observed from has been a direction within the disk. Our solar system is a flat thing, and we have spent the entire history of astronomy observing it from inside its own flatness. The poles of the Sun, the top and bottom of the heliosphere, the true vertical axis of the disk, all of this remains in territory visited only briefly by two spacecraft, neither of which was able to do more than sample a fraction of what is there. The first comprehensive view from above is still absent from the record. It is one of the few remaining gaps in the local map, and it is a gap that can be closed. The engineering exists. The trajectories have been calculated. What remains is the will to gather the resources and the patience to build the mission. The Sun has been waiting 4.5 billion years for the first sustained observation from above. It can wait a little longer. The mission is not impossible. The trajectories exist. What has not yet arrived is the funding, the political alignment, and the patient shared agreement among those who plan these things that the vantage is worth pursuing. It is worth pursuing. This evening has been, in its quiet way, about why. The geometry of our home, the three-dimensional structure of our local star, the true shape of the bubble we live inside, the appearance of the disk in plan view, and the orientation of the galactic sky from a direction we have never looked from. All of it waits on the one view we have not yet taken. The flatness of the solar system has shaped every photograph of the sky ever made. It has shaped every trajectory ever flown. It has determined the geometry of every observation, defined the horizon of every telescope, and set the boundary of what every mission could reach. The plane is not a mistake or an obstacle in any unfair sense. It is simply the natural, patient consequence of how a solar system once formed and how it holds its shape. We have lived inside that shape for the entire history of our species. We will continue to live inside it. The only question, the question that has been slowly working its way through tonight, is when we will choose to look at it from somewhere outside. The Sun turns slowly, as it always has, at the still center of the disk. The planets orbit as they have always orbited. The fast wind streams from the poles as it has always streamed. The current sheet ripples outward as it always has. The heliosphere holds its shape, whatever shape it is, against the surrounding interstellar gas. All of this has been happening and will continue to happen, regardless of whether anyone is watching from the directions that would let the watching be complete. The processes do not need the photograph. The photograph is for us.
And so the long, quiet consideration of the missing view becomes the gentle thread that ties tonight together. The plane is flat. The poles remain largely unseen. The bubble remains unmapped. The portrait of our home remains unfinished. The engineering exists. The will has not yet assembled itself. All of these things are true at once, and none of them asks anything urgent of you tonight. The universe is patient. The sun is patient. The disk has held its shape for billions of years, and it will hold it for billions more. The view from above will be taken when it is taken. The image will be added to the record when it is finally added. Until then, the architecture waits quietly. The trajectories wait. The spacecraft that might one day fly them waits as well. None of this requires anything from the listener tonight. And so we let the sun rest where it has always rested, turning slowly at the calm center of a disk that has held us for 4.5 billion years. The sky above its poles is quiet for now. The missing photograph is not exactly a loss. It is more like a promise, waiting patiently for the trajectories we have not yet chosen to fly. The flatness around us continues. The planets continue their gentle loops. The solar wind continues its long outward flow. None of this asks anything of you tonight. Let your breathing find its own easy pace. Let the long, quiet plane of the solar system settle around you. Let the directions above and below the sun stay where they have always been, patient and still and entirely unhurried.